Wei.
Sorry. Okay.
Wei.
Yeah, you flipped the mic. Yeah, that's right.
Xue Wei. Okay, our speaker today is very happy to have Xue Wei talking about the quest for new physics inside the sun. I'll take it away.
Okay, let me get the pointer works. Just a second. Sorry for that. It's, I cannot. But you see my screen, right?
Yes.
Okay.
Yeah.
Just forget about maybe just forget about the pointer. Let me.
Yeah, we can see the cursor, so it's fine.
Oh, you can see the cursor. Then it's much better. Okay, let me remove. Yeah, just bear with me 1 second. Okay. Okay, great. It's great pleasure to be here, to be UC Davis, even virtually, and happy to talk with you. And seems like not so many people, and trying to you are free to interrupt me, and I possibly speak too fast or speak like jump too much detail and just stop me. And today's topic is how do I search for new physics, especially dark matter or dark sector particle using the solar physics. And the particle I'm thinking about, the dark sector particle I'm thinking about, either is axion or dark photon. The axion can come in from the produced inside the sun, or like a dark photon can just convert to the radio signal and be observed by the radio telescope. So why we want to do that? Okay, so there's I don't want to give too much motivation for the like dark matter or dark sector stuff. This is just the only slide for motivation, and I think everyone knows we have tons of evidence of dark matter, but we don't know its identity for sure, and then we actually don't know what's its mass. This is actually not a motivation. Seems like tells me like you have 100. We don't know its mass. It can cover from like 10 to minus 22 eV to like solar mass. It's covering 100 order magnitudes. It seems like a very dangerous feat, but we break up into 3 classes just make things different method, normal method to search for them. And in the early time, we are focusing on particle dark matter, more like a particle. Think about TeV or 100 GeV dark matter. We have like direct detection, search, indirect, also collider to search for. One of the representative of model is called WIMP. And then right nowadays we are interesting like also very heavy dark matter, and dark matter is not fundamental particle. It's like massive compact halo. Massive compact halo. This is one of the well-motivated model is like called a primordial black hole. The mass is called I put a unit here is a solar mass. And the last one is today's focus is about a super light, and they behave like classical wave or classical field. And one of the well-motivated model is Axion. Also, I will talk about dark photon. So here's the outline. I have 2 papers related to the axions, the dark sector search in the sun. But first part is related to Xenon one-ton access. I will not only mention my paper in the first part of the talk. I will give you an overview of Xenon one-ton KeV access, and but only focus on ultralight particle explanation. Give you like for solar axion explanation, and the other thing is talking about axion, dark photon, dark matter. It also can explain the KeV access. So the second part of the talk, I will completely switch gear, talking about dark photon, dark matter. They are just crossing the sun and convert to the radio frequency signal, and it can be observed by the telescope. This is another paper I'm going to talk about. This is with Haipeng and Liu Jiang and Fapeng Huang. Okay, starting from the Xenon experiment. We all know Xenon experiment is for direct detection search. We built this kind of experiment deep underground, trying to treat all the background. And they are very famous to constraining. Right now it's constrained. They don't have discovered yet. They constraining like dark matter interacting with the nuclear, and especially spin independent interaction. I don't want to show you the plot. You already see the constraint plot and here, but the ballpark is like cross sections can go to 10 to the minus 47 centimeters square. If you like Z-Portal WIMP model, it's already ruled out by 6 or 7 order magnitude. So the Xenon experiment, we have several Xenon experiments, including LUX, Panda X, or today's talk, Xenon 1 Tom. From the theoretical physics point of view, they are roughly the same, and they made of like there are like two phases of xenon. One is liquid xenon, the other is gas xenon. And so their signal also have very time separate two signal. First, you have particle, either like dark matter or neutron coming in, hit the xenon and excite it or ionize it, and give you the first signal scintillation signal. This is we call S1. And then you do also some of the xenon will be analyzed, generate electrons, and you put a vertical electron feed to make the electron moving up, and then you see another signal S2. And this is an analyzation signal. And you see there's a photon and the beta, they will give you very similar signal. It's like there was S1 in the solid line and also S2 in the solid line. This is we call the electron recoil signal. I will come back to this point later. Just gamma and beta just give you roughly same signal. And in the up corner of the plot, it's just show you just a lot of data points with the S1 and S2 signal just map on this 2D primary space. For WIMP search, and we are considering nuclear recoil, and then electron recoil is just the background. We are trying to remove it by just eyeball this plot. You know, like one is most of them is some of them black, some of them is red, and using just statistic you can distinguish it. Okay, so we are not talking about nuclear recoil today. We're talking about electron recoil. This is all the black dot in the plot. So the events we will see. Let's collect all the electron recoil events. This is coming from 1 keV to 200 keV, and this plot is just give you the efficiency. So from the efficiency, you know that up to, if starting from 1 keV, your efficiency becoming sizable, and then you go to 2 or 3 keV, your efficiency roughly 80% or 90%. Okay, you see you get a lot of data from here. This is just the black point is just the data. You get to the data and you find there's a bump feature, there's something more smooth, and then you feed with the background model, and the background coming from like all the like atoms decays or excited atom decay to a ground state, or maybe just beta decay.
Is this the background and events that are identified as electron recoil?
Yes, that's right.
Okay.
Yeah, so some of the background they need to float in the normalization, but you see adding all the dotted line together seems like we fit the data quite well. And you have this spectrum, good. Then what you can do, like for example in the collider you have dimuon spectrum and you have smooth dimuon, you just do bump hunting, right? You search for new bump on it, maybe new bump coming from standard model, or maybe the new bump coming from the beyond standard. Definitely not the bump will have some size of it. So right now I just focus on like lower energy range, let's say from 1 to 30 keV, and I think the other region they don't find a clear signal, but in the region like the efficiency just rising, they see some excess over there. So 1 to 7 keV range, the expected events is 232 plus minus 15. And this is the uncertainty, and they observe is 285. Just roughly, if you think of 15 is the sigma, and roughly is 3 sigma discrepancy from the background model only. Okay, we have the data and we have access. The first thing we should do is not jumping into the new physics, right? It's how about some background? Maybe we miss some material. We maybe miss some background. Actually, in the Xenon paper they comment what's kind of standard, let's say called standard model background they can be contribute to the access. This is tritium. The plot you see is here is just the data, and the gray line is the background, and adding the dotted line is the tritium contribution. It seems like it fit the data reasonable good. The tritium is a really background is because its decay rate. Its decay rate is lifetime is like 12.5 year. This is awkward lifetime. You cannot. You know the xenon just run let's say roughly 1 year, so they have lifetime is too long, like they cannot decay. They cannot just decay promptly, but they are compatible to the exposure type of the xenon, so it means that they will decay sizably, and they still over there. To explain the access, you just need a tiny bit of tritium to explain it, and it seems like Xenon experiment cannot exclude this possibility. I'm not an expert on this kind of. Seems like the purification of things in the Xenon 1 ton, and there's one paper on this. I just put it the reference. Okay, the second thing, let's do new physics. Let's neglect the standard model explanation and forget about the possibility just the efficiency rising place is really in the corner. Let's think about new physics. And the Xenon experiment is built for dark matter search. Okay, let's do dark matter explanation. It's an electron Recoil, so we put dark matter interact with the electron. It's nothing very complicated, right? And I want to tell you how challenging it is, especially for the standard. Let's do the standard setup. Why it's not there? So we have bounded electron in the xenon. The bounded electron, just pure uncertainty principle. You know the momentum roughly like just 1 over r is the radius, and they are moving much faster compared to the dark matter. It's not like a nuclear recoil. You can treat the nuclear as at rest. So think about one region, like dark matter larger than the electron mass. This is the one region we are thinking about. And it's more like so it's like fast moving ping pong ball scattering with bowling balls. So the exchange momentum is just the ME times VE, and deposit energy when you can do the rest frame of the dark matter, and then shift that you get to the deposit energy is like ME times the velocity of dark matter. Okay, if you trust my computation, you just take the velocity and 10 to the minus 3, you get omega is EV. EV is 3 order magnitude off by compared to KEV. So let's do the lighter mass. So lighter mass becoming dark matter becoming ping pong ball. Then the total energy of the dark matter deposit is just the kinetic energy of dark matter. It's already, because mass is smaller than electron mass, so it's smaller than EV. Just conclude that this is not easy to explain the KEV access. So what's next? And so there are two branches to explain it. One is using like ultralight dark matter. The other is using the like dark matter particle, but they have different features. They can be boosted. They can be inelastic scattering. I put the particle part, the heavy dark matter explanation in my backup slides. If you want, I can send you the slides. But in this talk, I'm talking about just feebly interacting particle. I still just give you two classes. One is just light particle producing in the sun, and right now the light particle is smaller than KeV, and I will talk about production and talking about detection, and finally I will end up with astral bound. The other part is like just dark matter. Dark matter is KeV, and then they just moving to the detector and be absorbed or be scattered. Okay. So let me just do some simple estimation to convince you why we should consider local dark matter flux and the solar axion flux. There are many, many ways to produce these axions. And let's say the flux can come in from dark matter decay and annihilation. Let's estimate the flux. So dark matter decay from the galaxy center, put a keV dark matter, and decay lifetime is 100 times 10 billion year. So this should be, because there's constraints, we cannot, the lifetime cannot be shorter than that. And you can compute the flux, the dark matter decay to axions, the axion becoming keV and the energy. So the flux is n times decay rate times distance. So you put the number together, is you get 10 to the minus 8, 10 to the 8 per centimeter square per second. Yeah, this is small or large, just compared to we should compare to another value. Okay, dark matter annihilation from galaxy center. And you build a keV dark matter annihilation to axion plus other stuff. And put a cross section 10 to minus 26. Maybe this is just benchmark value for thermal dark matter. Maybe you can argue this is not it's too large, but this is just for estimation. Then you get the same thing, 10 to the 8 per centimeter square per second. How about the local dark matter flux? Local dark matter, just very simple, just number density times the velocity. This is local flux. The mass is keV, then you get 10 to the 13. So it's 5 automatically larger. The reason we consider local dark matter, this is one of the reasons. The reason, like, and then let's do solar axions. Let's put the coupling like Ga gamma gamma 10 to minus 10. This is roughly consistent with the astral bond, and you can compute the flux 10 to the 10. And actually, this slide already explained the result. The result is like using local dark matter. You can explain the excess. Using the solar axions, you can explain the excess, but you suffer from the other constraints because the flux is much smaller. That's actually the real simple reason to explain the result. But let's go step by step and to reach this result in the end. So the solar axion explanation, right-hand plot is just give you some benchmark model that can fit the Xenon access. But let me give you one more reason we consider the solar axions. Because the electron recoil access is keV, or like 1 to 5 keV. And the solar axion explanation is like they remove the one free parameter. The sun is temperature is keV, and they can produce the axion is keV, so you don't need to put the axion mass is keV. It's just, if it's smaller than keV, this is fine. Okay, and we want to study then we want to study in detail. We want to study how do they produce, how do they detect, and in order to do that, let's write down Lagrangian. The Lagrangian is just standard axion coupling. They have derivative coupling because of shift symmetry, and also the axion coupled to the like anomaly term F mu theory. Okay, this is the basic setup. Let's look at the production first, and then we do the detection. The production mechanism is you think about there's some ion, the electron in the sun, and the production is coming from ABC process. It's several process. Compton press, basically it's Brescia and also Compton scattering, and you see from the Feynman diagram over here. And also you can have Primakoff effect like photon scattering with offshore photon and produce axion using the AFF tilde operator. And then you also have ions, like there's a line signal is coming from, it's not relevant for the Xenon, not quite relevant for the Xenon experiment, but there's also, you have nuclear coupling, your excited ion can decay to the ground state, you produce the axion. But adding the three things together, you get the total flux. Okay, but this is, the process is also relevant for the stellar cooling. I will mention it again. After talking about the production and we want to get the signal rate, then we need to understand the detection. The detection is very simple. It's axion traveling from the sun and to the earth and to the detector and be absorbed by the electron, right? And so it will depend on only one parameter, just GAE. And then you multiply the two things together, you get the ABC effect where proportional GAE to the force. And the Primakoff effect just give you Ga gamma squared from the production GAE squared from the detection, etc. Very simple. And okay, after like this is Xenon in Xenon paper, it's like after like a very detailed data analysis and also just put everything in this 2D map. The blue region is the contour. The contour, like it can explain the access from the solar from the solar axions. Not hard to hard to understand this part. So this part is just means that they are uncorrelated with GA gamma, and it just means that this is because your GAE is pretty large. You can just using GAE to produce it and GAE to detect it. So you have some region like uncorrelated with GA gamma, and then you have this slope here. This is because your GA gamma is becoming larger, and actually you need use GA gamma to detect it, and also GAE GA gamma to produce it, and GAE to detect it. So you get this correlation. This correlation seems like consistent. Some of them is consistent with solar neutrino bond. The cluster bond is not quite can be irrelevant because you can put a mass larger than 10 millieV. The cluster bond is just removed or becoming just smaller. And the same worry to us is the stellar cooling bond. It seems the stellar cooling need like the coupling much smaller. If your coupling becoming larger in this region, it's already has tension with the stellar cooling. Okay, this is a little bit busy slides. Just let me give you some flavor how the stellar cooling affected give you the constraints. It's the cooling process is basically the same as the production process in the sun with Primakoff, Brest-Charlan, Compton. Okay. And then there was which kind of observable you can use. So right-hand side, you see the plot. This plot is the famous HR diagram, right? You see a lot of stars in the global cluster, and for the light star, and they follow some evolution. Or you run the other way, you run the stellar evolution code. Some of them just follow this line, like just go main sequence. The main sequence will go just the right branch, and then the helium fresh, and then horizontal branch. Basically, in the main sequence, you are bending the hydrogen, and in the right branch, you bending the hydrogen in the shell, not in the core. Like main sequence is in the core, and then you helium fresh means that you reach the core becoming degenerate. Your helium is bending, and the horizontal branch you bending the helium in the core. This is just different process, just different, just the evolution of the star. But you see, the right giant has a bending process. You see the tip of the right giant branch. They can be used to constrain the stellar cooling. Because you put more cooling into it, you will change the evolution. You make the helium fresh in much efficient. And the other thing is like also the other parameter, like you change the cooling, you will change the R parameter, and the number of R parameter is called the number of the horizontal branch divided by right giant branch. It's I will just explain a little bit in the next slides. But also you have in the end of the stellar evolution, you get a white dwarf, you have luminosity function, you have the rate of period change of white dwarf variables, all related to the stellar cooling. It's not related to detection, just the stellar cooling. You change the stellar cooling, you will change the stellar observable. You can imagine they suffer a lot of systematic uncertainties. Also, it depending on the model. Let me just tell you a little bit more about the R parameter. This R parameter is the ratio between the number of horizontal branch star divided by number of right giant branch star. Okay, these two numbers in the one global cluster, and the two numbers will proportional to the lifetime of the horizontal branch star divided by a lifetime of the right giant branch star. So you introduce the Primakoff process, and you just increase the energy loss, and it seems like the energy loss is more important. It turns out that the energy loss is more important than horizontal star, and you can decrease the R, just make the horizontal branch star as lifetime become shorter. And there's other thing there will be degenerate is like the helium abundance in the global cluster. This will affect the helium core or the evolution. And it turns out there's some degeneracy with Y and G10 square. The Y is the helium abundance, and G square is the coupling. So you can increase the G, also increase the Y, and they will just degenerate. But there's like 6.26, 0.41, and 0.112. How do they get this number? It's coming from like just this is not just first principle calculation. This is just pure stellar evolution modeling. And if you this means that this can be have some uncertainty, and some systematic uncertainty is coming from even whether we can trust the 1D model, and whether the other model can give you different parameter space, and also how do we assign uncertainty for this? How do we get the central value? And also all this depends. And all this uncertainty boils down to this plot over here. This seems like this is Y and GA gamma plot. The thing is like you have in the global cluster, you cannot measure the helium abundance quite well, actually. So people normally put the initial value, just the primordial value of the helium. But if you put this value, you get normally for the axion, you do just see like there's positive evidence of the axions. This some cooling needed to explain this thing. But if you just be more conservative, they can give constraints. And you see the solid line is their central value, and one dotted line is the 1 sigma, and two dotted line is 2 sigma. And then in order to get the constraints, and what the people did is like, let me just show you the result about the Xenon one-ton access by one group. Is for example, they focus on R parameter. They give you the tension is 19 sigma. I don't know how to take the 19 sigma to be very serious. It's all the modeling is like possibly can just go, they give you like 1 or 2 sigma, and they treat this systematic uncertainty as a statistical uncertainty, and then just also assume this Gaussian and then get this result. But anyway, this is just means that there's strong tension. It's no matter which value it is, just means that it's strong tension. I think this should be agreed. Okay. Just go back to Xenon one-ton access the contour over here, and we know the GA gamma GAE has correlated. Yeah, the region I highlight here, they are correlated. The correlation because of production and the detection using different operator. Okay, so what we all contributions, the small contribution we had is like we are thinking like the other process, the detection process cannot be neglected. The detection process is axion is producing in the sun. Okay, whatever is mechanism produced in the sun, and they travel to the Earth. They not only can absorb, but also can scatter with the xenon and produce the photon, because you have the AFF tilde coupling, right? So you can calculate the cross section, and also depending on some form factor, because the electron cloud, you cannot see the whole charge of the xenon. And the form factor is depending on the axial momentum or the exchange momentum, and or you can just change it as a screening effect. Roughly like 1 over R0 is like 4 keV. So you put your exchange momentum, typical momentum 3 keV, you get the effective charge is 5. And having this rate and having the rate, this detection rate, having the rate in the for the production, and we can combine them to get a prediction. And here is here the plot is, we fit the xenon data just using like GA gamma. It's like 10 to the minus 10 GeV, inverse GeV, forget about electron coupling, you still can explain the xenon access. There's one, let me just emphasize one thing, is this is the plot from UC Davis group. Is they do like KV photon can analyze the xenon, also the electron, and give you electron recoil. And let's look at just this plot and compare the right one, the downside one. It seems like they have different lines, just means a different electrofield. Actually, from eyeball, it seems like it's quite similar. It's from experiment side, it's hard to distinguish whether this is just the electron absorption, or it's absorbed the axion, or just are just the photon produced. That's the reason these two things these two signals should consider. Let's adding this inverse Primakoff process. What it looks like. So here's a plot. We trying to reproduce what Xenon 1 did, and we definitely cannot reproduce exactly the same. And they have the real data, and they also do 3D stuff and the marginalization and GA, but we get the roughly similar thing. And you see there's a uncorrelation band as GAE. Okay, and if we don't include in this process GA gamma, you get this slope over here. But if you increase, definitely you break degeneracy, right? You don't need a GAE, you just need a GA gamma. You can explain the excess. This is the thing we have. But you see that is here's a stellar cooling bound. We are close, but cannot completely solve the solve the stellar cooling constraint. Okay, how do we alleviate the stellar cooling constraints? There's many other thoughts about it. The one I put in the backup slides. There's one paper is talking about let's make the axions mass depending on temperature. So the axion mass can be smaller in the sun, but can be larger in the horizontal branch, larger than the very large, like MeV in the white dwarf, so that they cannot produce in the other star, but they can produce in the sun. That's one of the reasons, like you can twist your new physics model and make a temperature dependent. And the other thing is like there's a solar physics. Can we just twist the solar physics? It's this slides are based on the one recent paper is talking about solar physics. How do they produce axion? They never apply to the Xenon 1 access. I just plug in the number. I think it can explain the Xenon 1 access without suffering the axion the astral bond, because this is just very easy estimation based on their result. I don't think it's worth to write a paper, but it's worth to mention that it's. What's the magnetic field in the sun? It's actually in the right plot. They show that they imagine a very large magnetic field, 10 to the 7 Gauss in the inner region. The inner region don't have too much constraint actually. So the large flux. So you have magnetic field. You have photon coming and hit the magnetic field and produce axions. And usually you do resonance conversion and get a very large flux. So look at the axion flux and the dotted line. Let's say before we say that the flux is 10 to the 10. Right now it's like can be 1,000 times 10 to the 10. So it's 3 automatically enhanced. And then if you think an astral bond is the same, and then you are safe. But the question is the large magnetic field reliable? I talked to some solar physicists. They seem to say that they cannot hard to believe, but there's no constraints. This is the conclusion. And the other thing is, what about other stars? You're thinking about the magnetic field in the sun, but we know that other star also is coming from the main sequence evolution. Whether you can also have this large magnetic field in the horizontal branch, they also can enhance the signal. And we don't know, and this maybe deserves some further study. But this is just one interesting thought. And okay, we talk about the solar axions, and any questions? And right now we're going to talk about axion dark matter and to explain the Xenon access. Very just briefly mention the idea, but if I was just wondering whether have questions. Okay, if not, let's do the axion dark matter. The axion dark matter, the reason I already tell you why the dark matter can be a good thing, because the flux is larger. The stellar cooling bond give you like the GAE bond 10 to the -3, and the solar axion to explain the Xenon, you need 10 to the -12. There's a 1 order magnitude mismatch. But the local flux, and it's much larger, 10 to the 13 per centimeter square per second, and solar axion flux is roughly 10 to the 10. Seems like from this plot, like Xenon produced, is like they can get the constraints. Also at the KeV, they can really just explain the excess. It seems like they don't suffer from the astral bound. There was one thing to mention is like they needed axonal decay. So it means that they need the axion coupled to 2 photon. It's pretty small, and using maybe you need a KUKA model, maybe just the photon phobic or like anomaly free stuff to make the AFF tilde small. This is just make the axion becoming stable and as a dark matter. Okay, the other possibility is the dark photon dark matter. Let me just using this slide just introduce dark photon dark matter, and I will use the same like Lagrange before. It's just you have A prime and then you have the F prime F mu square. Then you have mixing of the dark photon and the photon, and the epsilon. You think about this coupling, and you put the mass of the dark photon. This is just coming from Stubbe mechanism. So the thing is like you have the dark photon, dark matter moving to the detector, just absorbed by electron. And if you want to use solar dark photon, this is already ruled out or doesn't fit the data quite well. But if you use dark photon, dark matter, you can it seems like you see the contour of here seems like consistent with other bound, and can explain the Xenon one-ton access reasonable well. Okay, the last possibility the last slides I want to mention, the other is like U1B dark photon dark matter. It's still it's hard to explain the solar axion coupled to the U1A prime. It's because the reason is it's very simple. It's like because let's think about this is in the star, the thermal photon can decay to the A and the A prime, and easily this can be just the stellar cooling bound. But we can use U1B dark photon as dark matter, and different from the dark photon absorption, they actually U1B dark photon, they just scatter with Xenon and produce a photon. This is a photon signal in the detector, and the coupling is 10 to the minus 10. It's consistent with the experiment, other experimental constraints. Okay, so let me summarize here for this part. It's like solar axions. We have GAEE and GA gamma, but the inverse, there are 2 couplings. They can just we need to consider to explain the Xenon one-ton access. The inverse Primakoff in the detector should be included, and even we included, we still suffer from the solar axions stellar cooling bound. In order to remove the bound, you can just change. You can have a new physics, or you maybe just twist the solar physics. You put a large magnetic field in the solar physics, and for the reason is the other thing I mentioned quickly is dark matter. Ultralight dark matter is also can explain the excess. Just using because just the reason is like the flux is much larger than the solar axion. Let's do the part of Xenon one-ton access. Right now, I will completely switch gear and talking about dark photon, dark matter across the sun. Here's the basic idea: the dark photon, dark matter coming to the sun and then convert to the photon. And actually, it's the photon is a radio frequency, so it's detected by the telescope. Okay, how the dark photon produced in the early universe? Let's talk about his history. There was some similarity between dark photon and axion. There was some difference between them. First, the thermal production doesn't work because the coupling is pretty small, and you can never thermal produce them. If it's thermal producing, it means that the relativistic you cannot become a dark matter. And the misalignment usually works for the axion. The axion just misaligning get some spectrum, some offset during inflation. They can be becoming contribute to dark matter radical abundance today. But this doesn't work for the vector because the vector redshift as a to the minus 2 during inflation. But they can produce from the inflation perturbation, of A prime, and especially the longitudinal mode. They can explain the the dark matter radical abundance if the mass is 10 to the minus 6 eV or larger. The other mechanism is think about the axion. Let's say you have axion already becoming dark matter, it's like a non-relativist like, and they can just resonance convert to the to A prime in the early universe due to its oscillating in the bottom of the potential. And there was several papers coming out in the same day in the archive, and they are talking about the same idea. The last possibility is by Andrew Long and Lian Tao, and they are thinking about just cosmic string producing like your U1 symmetry breaking, and your A prime sometimes related to the U1 symmetry, and the U1 symmetry breaking give you a cosmic string in the early universe. The cosmic string, and they were connecting, they were oscillating, they were just decaying to graviton and decaying to the A prime. The A prime can be the dark matter candidate. Okay. Already talk about their history. Let's talk about the search. The search, there's many search you can do for dark photon, and also you can apply some of the axion search to the dark photon. And here you have CMB constraints and effective, because dark photon can just resonantly convert to photon in the CMB time or before after. Then they will distort. You have extra soft photon in the spectrum. They can distort the Boltzmann distribution of the photon. This can be constraints. And also you have extra photon. You can dilute the thermal abundance of the neutrino. This will be constrained by ineffective. And the other constraint is coming from the helixscope, like you produce A prime or longitudinal A prime, and they can constrain by the xenon, and this is the constraints on the right corner. And also you have helixscope like ADMX. You have cavity, also the visible DMX, also similar idea. It's like you have cavity, and the dark photon and the dark matter is inside of the cavity, and the convert to photon can be observed or can be constrained. This is the 2D map over here. There was still some region unexplored, and and especially like for future, you have DM radio will cover some of the region of this space. So all idea is trying to think about it can be use star to constrain. Let's give you some the idea how the idea generated. Let's just give you some background. As the idea is generated by reading several papers on axions. So ultralight boson searches in the star, and the axion we know that they can convert in the star. You have axion dark matter coming, and you have A F tilde. F tilde is just A times B feed times photon, and axion can convert to the photon or radio signal, and in presence of magnetic field. So let's find out where the star has the largest magnetic field, 10 to the 14 Gauss for neutron star, some very magnetic star, and the axion can be converted in the photon in the magnetosphere and be detected right by the radio telescope. Okay, then also you can apply some similar idea to the magnetic white dwarf, and that's for axions. So how about dark photon? The dark photon, we don't have the AFF tilde coupling. Is just the F prime, right? F mu mu F prime mu mu by epsilon. So we don't need a very extreme magnetic field. Then if we don't need a magnetic field, then we just need a star very close by. The close the better. The close the flux is larger. So we use the sum. And we want to. So the idea is like you have some dark photon coming, and the resonant converge to photon. So when we say resonant conversion, means that the dark photon mass should be equal to the thermal mass of photon. Let's compute the thermal mass of photon. In the plasma, it's like 4 pi alpha me, number of electron, number density of electron divided by me, and then square root of it. And in the plot you see here, the number the sum is like they have some distribution of the number density of electron. This is basically like it's going all the way down to you reach the outer region, right? It's basically just scan. You scan different dark photon mass, or you scan different thermal mass. And the blue line, you see that the blue line is changing from like 10 to the 13 and it goes to like 10 to the 7. It's a pretty broad range. And then let's just convert to the thermal mass, you see that in the coronal region, the thermal mass 10 to the minus 6 eV, or here is 10 to the minus 7 eV, and in the coronal sphere, you get 10 to the minus 4 eV. So basically, this is the plot already just translated the number density of electron to the thermal mass of the photon, and also can convert to the mass of dark photon. So this plot already give you which kind of range we will which kind of range of dark photon they will the sun can probe. Okay, we let's compute the rate, right? The rate you can compute just using by solving the linear wave equation, but we have a more simple way to compute it, right? We know that let's do like just like quantum mechanics, QFT stuff. Let's do scattering. Actually, it's not scattering; it's 1-to-1. So idea is similar. It's like you do the matrix element square, and you have the energy momentum conservation delta function. You have phase space of final state, and divided by 2 omega, just the normalization, and time dt. It means that we not only compute the rate, we compute the probability. We integrate dt, and the final result will definitely depending on the epsilon square and your coupling square and the mass and the inverse of the velocity, and also the number density of the photon, number density of electron. The other thing, we figure out the rate, we want to figure out the directions. What's the direction? Actually, this is the direction is like we first need to assume spherical symmetric. It means that the density only depending on radius. The converted photon will just follow the normal direction. Why is that? It's just a reflection law. It's because in the plasma, the reflection index is equal to the group velocity of radial wave, and at the resonance conversion, the refraction index is or we say the group velocity 10 to the minus 3, 10 to the minus 2. And then you just compute the sine theta times n is equal to constant. After you remove, after the photon travel outside to the conversion, the resonance region, their n is roughly 1. And then your sine theta is, before your sine theta is 1 times a very small n. Right now, your n becoming 1, so your sine theta becoming small. The sine theta is smaller than 10 to the minus 3 and 2 10 to the minus 2. So immediately after they travel outside the resonance region, they will just become in normal direction. It seems like in this, you can imagine just a hedgehog image. It's like in the center, you have very in the center of the sun, you get a much larger flux. But this is really ideal case. Actually, in the sun, the sun, you can imagine the density is fluctuating, and you have a lot. It's not a uniform dispute, and the converted photon is actually we have to take a very conservative assumption, assume it's isotropic. So the last thing we want to talk about signal is the absorption. You generate the photon, you want to propagate outside the sun, right? You don't want be absorbed in the middle, or they are in other channels we calculate the optical depth. There are two kinds of scattering is important. It's like inverse Bragg challenge and the confidence scattering. And in terms of the inverse Bragg challenge is very important. This is just the result over here. You have the normal cross section over here depending on density, and you get the log term coming from the long wave distance, long wave effect of the Coulomb scattering. So what's the effect? Its effect is boiled down to this plot you already see. It's like in the chromosphere, and or in terms of the mass, is the A prime mass is in this range. You can have a resonant conversion, but the inverse Bragg challenge is pretty efficient. They can just block the region. But in the coronal region, your photon is produced that they can just move outside. That's and we already have signal flux density. The signal flux, just I told you, you have the property, the conversion. You divide by, you times the maybe you consider the absorption, and then you divide by d square. D is the distance, is 1 AU, right? Earth and the sun is 1 AU square, and divided by the resolution. The B is just resolution, or which one is larger, signal width. If the resolution is larger, you're just using resolution. The signal width is larger as using signal width. Usually, normal case resolution is much larger. And we want to derive what's the detection probability, right? So we want to consider system what's the flux from background? So basically, it's bump hunting. You have some background you view, and you bump hunting a signal from the photon or radio for signal. There's a systematic equivalent flux. The flux is, we separate two parts. Is temperature divided. They phrase it this way: just temperature divided by A effective is effective area. Effective area, you can think about just the area of the radio telescope. Temperature, they divide by two parts because they just want to separate the one is from the sun and one is from the other noisy environment. For the T system, it's including the CMB, it's coming from the surface emission in the Earth, it's coming from the cloud emission, it's coming from even in the rain, and they can give you all the T system. And also, because your telescope is aiming at the sun, you get also very noise background from the sun emission, right? And usually your telescope sometimes don't want to, in order to observe other stuff, you want to avoid the sun. But if you observe the sun, we are saying that they possibly have signal. So minimum detected flux is the system equivalent. The most naive way is your signal is larger than your system equivalent flux, you get a signal. But we have the central limit theory, and it means that if you observe long time, your times resolution means that you roughly speaking, you can just think about you repeat the analysis n times, and it's like b times t observation. You just decrease the minimum detected flux density, and your signal can be much smaller and it can be detected. Okay, here's some data we want to use for use. For example, in the future we have SKA experiment. This is already committed to build, and today we have LOFA experiment we can use. So let's look at the final result. The final result is the gray region is the constraints you already see in the previous slides, and this is the current constraints. The color shaded region is the reach like dark photon can do. And the existing experiment LOFA, actually we don't do the real data analysis. We just take their parameter and think about they run 1 hour, what's the blue region? This is the blue region they will cover. And if it's 100 hours, they can reach like here. Actually, this analysis is very simple, just S mean. We compute S mean smaller than S signal, then we can get the result. And this cutoff, there's a lower cutoff because the experiment cannot go lower, and there's higher cutoff because as I told you, there's the absorption which we have to consider. And in the future, as SKA, if they aiming at the sun, and they can get much better constraints and also covering different mass range. It seems like we don't need to build a new experiment, and the existing LOFA and the future SKA for other they build for different purpose. They can just swap this region like 1 order, 2 order to 3 order, 2 order to 4 order magnitude, and compare to the current constraints. This is just to emphasize, this is just the plot for Epsilon. Actually, the reach, because this rate is possibly proportional to Epsilon square. Actually, the limit is very strong. So the next clear project to do is like really apply using the LOFA data if they are available, or apply some time in the LOFA to get to do the list kind of simple bump hunting analysis to in order to reach this region. Possibly we can discover dark photon in the future. And let me conclude. And I give you some overview of Xenon one-ton access. I put some slide talking about high mass dark matter, explained the Xenon one-ton in the backup slides. But here in this talk, I focus on solar axion, the ultralight dark matter. And still, I mentioned, give you some flavor about the astro observable constraints, especially R parameter. I think they suffer from a lot of systematic uncertainty, and the paper seems to treat all the systematic uncertainty as a statistical uncertainty. Just think about, and then you get very strong constraints. But we should admit that still the solar axion really has tension with astro observable, and in order to, there are several ways to alleviate it. And the last thing is like dark photon, dark matter across the sun. We are thinking about using the radio telescope if they are aiming at the sun, and can we just using to probe the new physics. That's all. Thank you.
All right. Let's unmute and thank Xue.
Thank you.
Any questions?
I have a question. Can you go back to the previous slide?
Previous slide.
Yeah.
This one.
So what about the LDMX experiment?
LDMX. Which one? So which kind of experiment is a haloscope?
No, it's pushed by Slack, Natalia Toro and Philip Schuster. Like a light dark matter search, something like sub-GeV.
It's not either.
Oh, probably that's not.
Not
that's
in the mass range, or either it's the coupling cannot be as. This is I didn't include all the experiment. I put the stronger experiment in this mass window, and I didn't. Yeah, there was other mass window as well. Also the coupling. There's other constraints is coming from the other experiment, but not stronger as the CMB constraints, I think.
Yeah, sure.
It's
Probably
not,
that's
not considering that it's not. It's much heavier, I think.
Oh, it's much heavier. Okay. So
That's like GeV, I think, MEV, GeV.
I see. That's completely different region.
Can
Yeah,
I ask a quick? Sorry, can I ask a quick question? Because I'm sorry, but I have to go pretty soon. I think there's a basic point that I kind of missed about the radio telescope thing. Just 2 slides ago, I think your slide 35, you had a whole bunch of these backgrounds, right? And
Yeah.
just from this picture, I would guess that the background is pretty uncertain.
Yeah,
but I didn't understand how do you so how is it that can you say just a little bit more about how you get your sensitivity estimate?
Oh, there's uncertain, but the dominant one is the solar one. So first, the dominant one is from the sun. Actually, the sun is really bright. The dominant one is the sun, and we need to just observe in the quiet sun region. Seems like you get all the uncorrelated the photons, radio photon signal is basically just smooth spectrum in the background. And then you just do bump hunting, right? It's depending on what's the signal flux.
So it's just the frequency. There's a frequency band, and so as long as it's above the smooth background, you can do sort of signal over root background underneath the bump or something.
Right.
Okay.
It's just depending on the really depending on signal size. It's actually we forget about the square root of n. We just compare the flux, the sound flux, and the signal flux. They are in some range. Is already compatible, and just this is pretty. It's because of resonant conversion. Actually, it's the conversion is pretty large, and also the dark matter flux is pretty large.
Okay, so I've got to go, but I hope you guys will stick around a little bit longer. I've got to go to my other meeting. Thank you very much. Thanks for the talk.
Thank you.
Yeah.
Thank you for the question. Nice to meet you. Any more questions?
Can you comment on, you had a slide with the temperature of the sun?
Oh, temperature of the sun. It's why is decreasing?
Yeah.
It's a really the puzzle, and no one knows why. It's very funny, right? Its temperature is smaller and then increase. I don't know. As we also noticed this effect, but it seems like this is a puzzle one for the solar physicists.
Is it really measured to be that sharp?
Oh, is it?
It just goes vertical there. Is this data or a simulation?
This is the. I think this is data. I don't know whether this I cannot answer whether this is why this is too sharp. I guess this is just physical change, right? Yeah, let me go back. Maybe I give you more confident answer after the talk. I'll send you email.
Okay.
To tell you exactly. Okay.
Maybe you can go to discussion section, John.
Okay. Well, let's thank the speaker again.
Thank you.